Black holes, the universe's ultimate trap. They sound like pure science fiction, cosmic vacuum cleaners that suck up everything around them. But they're real, and the more you learn, the weirder they get. So what exactly is a black hole? Imagine taking a star bigger than our sun and crushing it down until it's smaller than a city. All that mass, all that gravity, squeezed into one tiny spot. At the heart of the most extreme cosmic phenomena lies the black hole. But what is it? Imagine a star, many times more massive than our sun, at the end of its life. When its nuclear fuel runs out, the outward pressure that supported it vanishes. Gravity wins decisively. The star's core collapses in on itself with unimaginable force, squeezing an immense amount of matter into an infinitesimally small space. The gravitational pull becomes so powerful that the escape velocity, the speed needed to break free, surpasses the speed of light itself. This creates a boundary in space-time known as the event horizon. It's not a physical surface, but a one-way door. Think of it like a river flowing towards a colossal waterfall. Far away, you can navigate freely. But the event horizon is the point where the river's current flows faster than you could ever swim. No matter how powerful you are, the current will inevitably pull you over the edge. Once you cross this threshold, you are gone from the observable universe. All possible paths now lead to one place, the center. And since not even light, the fastest thing in the cosmos, can escape this gravitational prison, the object itself is completely invisible. It is a perfect void, a silhouette against the stars. That's why it's black. But the true weirdness of black holes goes beyond just pulling things in. According to Einstein's theory of general relativity, gravity is a curvature in the fabric of the universe, what we call space-time. Imagine space-time as a stretched rubber sheet. A planet creates a small dimple. A black hole, however, isn't just a dimple. It's a puncture, a bottomless well-warping space and time to their absolute limits. This extreme warping has a profound effect on time. The stronger the gravity, the slower time flows, a phenomenon called gravitational time dilation. This leads to a bizarre paradox. If we watched you fall towards a black hole, we would see you slow down as you approach the event horizon. Your image would get redder and dimmer until you appeared to freeze at the edge, suspended for eternity. But from your perspective, you would feel no such pause. You would cross the event horizon in a finite amount of time, unaware that to the rest of the universe, you've become a permanent, frozen fixture. So, what happens after you cross that point of no return? Here, our current understanding of physics breaks down. General relativity predicts that all the matter is crushed into a single point of infinite density called a singularity. Before you could ever reach it, the tidal forces would tear you apart in a process gruesomely named spaghettification. The gravity at your feet would be so much stronger than at your head that you'd be stretched into a thin stream of atoms. What lies at the singularity itself? This is one of the greatest unsolved mysteries in science. At the very center of a black hole lies what's called a singularity, a point of infinite density where our current understanding of physics completely breaks down. Imagine taking the entire mass of a star, billions of times heavier than Earth, and crushing it into a space smaller than a single atom. Then, keep crushing it, infinitely. The result is a region so extreme that the two pillars of modern physics, Einstein's general relativity, which governs the very large, and quantum mechanics, which governs the very small, give contradictory answers. General relativity predicts this point of infinite density, but quantum mechanics suggests that such infinities shouldn't exist in nature. This clash is one of the most profound problems in science. Here, space and time themselves stop making sense. According to Einstein, gravity is the curvature of space-time. At the singularity, that curvature becomes infinite. It's not just bent, it's broken. The very concepts of here and there, before and after, lose their meaning. To truly describe what happens at this point, we need a new, unified theory of quantum gravity, a theory of everything that can reconcile these two great ideas. This is the holy grail of theoretical physics, and the singularity is its most extreme testing ground. The breakdown of known physics allows for some mind-bending speculation. Some scientists, working from the mathematics of relativity, theorize that black holes might be gateways. The idea of an Einstein-Rosen bridge, or wormhole, suggests a black hole's singularity could connect to a white hole in another part of our universe, or perhaps even another universe entirely. While a black hole only lets things in, a white hole would only let things out. However, these theoretical bridges are thought to be incredibly unstable, collapsing the instant they form. So while they make for great science fiction, traveling through one remains firmly in the realm of fantasy for now. But perhaps the most vexing mystery is the information paradox. A fundamental rule of quantum physics is that information can never be destroyed. The universe in principle keeps a perfect record of everything that happens, but a black hole's event horizon is a one-way door. What happens to the information of an object, its mass, spin, composition, once it falls in? For decades it was thought to be lost forever. The problem got worse when Stephen Hawking discovered that black holes aren't truly black. They slowly leak energy, called Hawking radiation, and over unimaginable timescales, they can evaporate completely. If the black hole disappears, what happens to the information it swallowed? Does it simply vanish, violating the laws of quantum mechanics? This is the paradox. The leading solution is the holographic principle. It suggests that the information about what falls in isn't destroyed, but is instead scrambled and encoded on the two-dimensional surface of the event horizon, like a cosmic hologram. As the black hole evaporates, the Hawking radiation subtly carries this information back out into the universe, preserving it. The 3D object is gone, but its informational blueprint survives. And these cosmic mysteries aren't confined to rare, distant monsters, they're everywhere. We now know that black holes are not just oddities but fundamental components of the cosmos. They are the architects of galaxies. At the heart of almost every large galaxy, including our own, lurks a supermassive black hole, millions, even billions of times more massive than our sun. These giants act as gravitational anchors, their immense pull holding the galaxy's stars in their orbits. Their activity can regulate star formation across the entire galaxy, sometimes triggering bursts of new stars, and other times blowing away the necessary gas with powerful jets, quenching star birth for millions of years. The one at the center of our Milky Way is called Sagittarius A. We can't see the black hole itself, but we can see its shadow cast against the swirling superheated gas being pulled into the abyss. A direct confirmation of a cosmic titan, 4 million times the mass of our sun, sitting in our own galactic backyard. In 2019, humanity saw the impossible. This image, the first ever of a black hole, may look like a blurry cosmic donut, but it represents a monumental scientific achievement. It was captured by the Event Horizon Telescope, a global network of radio dishes synchronized to create a virtual telescope the size of our planet. The challenge was like trying to photograph an orange on the moon. What we're seeing isn't the black hole itself, but its shadow. That glowing orange ring is superheated gas and plasma orbiting the abyss at near light speed. At the center is the event horizon, the point from which no light can ever escape. This single image was more than a picture. It was the stunning confirmation of a theory proposed over a century earlier. Albert Einstein's equations of general relativity predicted these bizarre objects, but for decades they remained a mathematical curiosity. The portrait of the supermassive black hole in galaxy M87, 55 million light-years away, transformed science fiction into scientific fact. It was proof, forged by hundreds of scientists across the globe, that the monsters in the dark are real. So what would happen if you fell into one? Near a smaller black hole, the tidal forces are extreme. The gravitational pull on your feet would be so much stronger than on your head that you'd be stretched like spaghetti, a process scientists call spaghettification. You'd be torn into a stream of atoms before reaching the edge, but for a supermassive giant, the tidal forces at the boundary are gentler. You could cross the event horizon, the point of no return, completely intact. This isn't a physical surface, but a one-way door in space-time. Once inside, space itself is falling into the center faster than light. All paths lead to the singularity. Your destruction would be swift and absolute. But here's where things get truly strange. From your perspective, you fall in and are gone. For an observer watching from a safe distance, something entirely different happens. Due to gravitational time dilation, we would see your clock slow down as you approach the horizon. The light from you would be stretched, becoming redder and dimmer. We would see you slow, fade, and appear to freeze at the edge for eternity, never quite crossing over. So which reality is true? This is the black hole information paradox, a deep conflict between general relativity and quantum mechanics. Quantum physics insists that information can never be destroyed. So, what happens to the information that makes you? Is it lost forever? Is it encoded on the event horizon like a cosmic hologram? It's a cosmic magic trick, and nobody agrees on where you'd end up. Solving it may unlock the next great revolution in physics. So here's the wild part. Black holes may not just destroy, they may help explain how the universe itself works. They might hold the keys to quantum gravity, to understanding time, even to discovering new universes. Black holes are less like vacuum cleaners and more like cosmic mysteries, terrifying, beautiful, and essential to the fabric of the universe. So, do you think black holes are the end of the story or just the beginning of something bigger? Let us know in the comments. Hit the subscribe for more random science.